Hi, the post just came and it's a box, generally. I think there's a multimeter inside, so let's go ahead and check this out. In the box we've got a multimeter, which is the Brymen BM860 series, and some promotional materials. I think I'll have to stick them on some piece of paper to actually read something, but that's nice. They sent a catalog. I have ordered the BM867 model because it was a bit cheaper and it didn't really lack any usable features for me. And the only thing that it differs from the 869 is that it lacks the 100 kHz AC and DC voltage bandwidth. It has a slightly less DC accuracy. It doesn't do variable frequency drive measuring, and it doesn't support the thermocouples. But that's not really necessary for me, so I decided to buy the 867. Inside the box we've got the digital multimeter, the industrial test leads, the user manual, and that's all, because the thermocouple is only for the 869 model. Let's check it out then. That's the multimeter. A couple of cables which have these useful covers, so you can you have only the tip exposed, so you don't accidentally short anything out. We'll get to this in a moment. Let's take a look at the meter itself. I think it has a battery included, so yeah, let's put it on. Well, the battery looks okay. Yeah, we've got the AC voltage, the DC voltage, and the DC millivolts, and the AC millivolts also. There's a diode check, capacitance meters, resistance meter, milliamps, amps, and microamps meter. So all the things that proper multimeter should actually have. Let's measure something that my old multimeter couldn't do. So it's a very tiny current of 1 microamp. And in order to measure it, we need to build a tiny current source that is going to deliver that microamp for us to measure. After powering the whole circuit, I must say that we are exactly spot on. That's 1 microamp. The last digit is switching between 0 and 1 because the last digit on digital meters is always inaccurate. So you need to keep this in mind when using these. But overall it means that there is 1 microamp exactly flowing through this node, and that we have achieved what we wanted, a quite precise constant current source. So a couple of words about the circuit. It's a current source. It's a very simple circuit. There are integrated circuits which do this job way better, but this one is enough for our needs. It has two parts. The first one is the voltage divider, and the second one is the emitter follower. And it works like this. The voltage divider sets 2.5 volts on the base of this transistor. Then the transistor drops enough voltage to set 2 volts on its emitter. And this resistor is calculated in a way that it's gonna give 1 microamp when there are 2 volts applied across it. And you can calculate from the equation that resistance equals the current over voltage that this resistor has to be 2 megohms. In case of this transistor, which has a quite big HFE coefficient, you can disregard the base current, and that means that the emitter current is going to be equal to the collector current. So if the emitter is giving out 1 microamp, that the collector is sourcing 1 microamp too. And that's basically everything about the circuit. You can modify it very easily. For example, you can replace this voltage divider with a potentiometer, and this is going to give you a current source that you can actually adjust. Apart from that, you can power the voltage divider from a stabilizer. It can be an emitter follower with a Zener diode, for example, and this is going to result in a current source that is independent of the supply voltage, so it's gonna give the same current as long as the voltage is bigger than a certain amount you need to have your regulator working. So overall, I find this meter very nicely designed and very easy to use. It's also quite accurate because it showed the exact value that we've calculated before. That's all for this episode. I hope you like it, and see you next time. Cheers!